Okay, welcome back, and we're going to dive straight back into where we were on page 135, and we're going to look at the values at other points. So at -2, what about the function value at -2? Is it positive, negative, or 0? It's definitely negative. We're below the x-axis. The y value of this point is actually -9. What about the value of the gradient at that point? Well, it is 0 because it's a turning point. What about the value of the second derivative? Well, we're on a piece that looks like a cup, concave up, positive, second derivative. Okay, let's look now at the point -1, this point over here. All right, -1 is just over here. There's the point of inflection, so we're just over here, over there. The y value is negative, the function value is negative. The gradient is the function increasing or decreasing. It's going uphill or downhill. It's going uphill. Are we on a piece of curve that looks like a cup or like a frown? Like a cup, second derivative positive. Right, now at -5/6, what's the function value? Is it positive, negative, or 0? It's definitely negative. What about the gradient? The gradient's positive because the graph is going uphill. What about the second derivative? Now, at a point of inflection, the second derivative is 0. Okay, next up we're going to look at 0. Okay, so we're talking about this point over here. Is the function value positive, negative, or 0? Well, it's actually 3, so it's positive. What about the gradient? Well, the gradient, we're talking about this red point over here, the gradient is positive. And then lastly, the second derivative, are we on a concave up like a cup or concave down like a frown? Concave down like a frown. So positive and negative. All right, at 1, we talk about this point over here. That's a significant point because the function value is actually 0. That point is actually, we call 1 a 0 of this function. Okay, it's where it has a value of 0. Also called a root, also called an x-intercept, also called a solution. Okay, so the function value is 0. The gradient, is the gradient positive or negative if the graph's going downhill? Negative. The second derivative, are we on a concave down like a frown or concave up like a cup? We concave down like a frown, so negative. Negative, frown, sad. Up, positive. Second derivative, positive. If you're feeling concave up, you're feeling upbeat. Okay, 7/6 is somewhere over here. The function value will be negative. The gradient will be negative, and the second derivative will be negative. Okay, notice that on this cubic function, the concavity only changes once. All of this, positive second derivative, the graph is concave up to there, and then negative second derivative, the graph's concave down from the point of inflection onwards. Okay, I'll just show you on the graph. Okay, concave up. This graph is concave up like a cup to there, and then it's concave down like a frown from there. Okay, all right, we spent a lot of time on that. It's important, it's really important. If you can understand it, then you don't have to learn it. Okay, right, now this says determine any stationary points and then work out what are they. Right, so what we're going to do, we're going to find the gradient, okay, f dashed of x. 18x squared plus 2x minus 20. We're going to make it equal to 0, and the reason we make it equal to 0 is to find stationary points. At stationary points, the gradient is 0. Okay, right, so this, I'm going to divide everything through by 2 here. I think it'll be a bit easier to factorize. 9x squared plus x minus 10 equals 0. Okay, this is in fact going to factorize to, I think 9x and x and 10 over here and 1 over here. All right, and so we're going to get plus 10x from the inner pair and minus 9x. Okay, so there it's fully factorized. And so we've got stationary points, all right, at 1 and at -9/10. So -10/9 to make that bracket 0. Okay, now I'm not going to do this here But if we wanted the y values of these points, we would put those numbers into the original equation. Remember that f of x is actually the y of f. Okay. All right, we can put 1, and 1's easy to put in. 6, 7, minus 20 is minus 13, minus 12, minus 25. Okay, I'm not going to bother to work this point out here by putting the negative 10 down. But now I want to know which of these points is a minimum and which one's a maximum. So what we're going to do now, we're going to work out the second derivative. I can use a red pen for the second derivative. All right, f double dashed of x is just, I'm just differentiating this. It's 36x plus 2. Now, if I work out the second derivative at 1, at that stationary point, do I get a positive or a negative number? I actually get 38. Now 38 is a positive number, which means that the graph is like a cup, which means that this is a minimum turning point. Okay? If I put negative 10 over 9 in here, all right, I don't know, I'm not going to work it out exactly, but we can see we're definitely going to get a negative answer. Right, and because it's a negative answer, it means the graph is concave down like a frown, which means that this point is a maximum. So what we are doing, we're using the second derivative to tell us about the nature of our stationary points. Right, we're going to ask you to pause the video, try the next 3 yourselves, and then let it play again and see how you went. Okay, so let's look at this next one. The first derivative is 3x squared minus 4x minus 4. Now, to find stationary points, we want that to be 0. So we're now going to try and factorize this, and in fact it's going to be 3. The only way 3 can factorize is 3x and x. 4 can factorize with 4 and 1, or with 2 and 2. And it's in fact going to be 2 and 2. We're going to have a minus 2 here. That's going to give us negative 6x plus 2. So what we now know is we know that at x equals negative 2 over 3, the gradient is going to be 0. All right, negative 2 over 3. And also at x equals 2, the gradient is going to be 0. Now remember, these are points. Where would I put those values to find the actual y values? I'd put them back into the original function. This is the function value, not the gradient, the function value. Okay, I'm not going to do that. It's just time consuming and we don't really need it for what we're doing here. What we're going to do now though is we're going to look at the second derivative. The second derivative is actually g double dashed of x is actually 6x minus 4. Now, if we put 2 into the second derivative, okay, we're going to get 12 minus 4. We're actually going to get 8. I'm not really worried about the fact that it's 8, but I'm worried about the fact that it's positive. Positive, the graph is concave, up, which means that this is a minimum turning point. If I put negative 2/3 in here, I actually get a negative answer. So g double dash, the second derivative at negative 2/3 is negative. All right, and therefore we're dealing with a maximum. Okay, right. Now let's look at number C. Once again, we're going to work out the first derivative, y dash negative 3x squared minus 14x. We want that to be 0. So don't divide by the variable. We never divide by a variable. Let's divide everything through by a negative sign, so in other words by negative 1. So we're going to get 3x squared minus 14x equals 0. And so now we can factor out an x. 3x minus 14 equals 0. So one of our turning points is 0 something, and that one's very easy to work out. If you put 0 into this original function, you get 36. I'm not going to work out the y value of the other one. We get the x value is going to be 14 over 3. Okay, right, we could get that y value by putting 14 over 3 in here using our calculator. Let's work out the second derivative, okay? So we're going to work out y double dashed. And y double dashed is actually, if we look, it's negative 6x minus 14. Now, when we put 0 in, we're going to get a negative value. And if we get a negative value, the graph's concave up. So this point over here is actually a maximum. When we put 14 over 3 in here, we actually get a negative answer. When we put 14 over 3 in here, we're actually going to get a positive answer. 14 over 3, no, we're not going to get a positive answer. Negative 6x, sorry, it's not negative 6x, sorry. It's 6x minus 14. My apologies. All right, the second derivative is 6x minus 14. So when we put 14 over 3 in, we're going to get a positive value, concave up, like a cup. This point is a minimum. Okay, and then the last one, and the last one's important because actually our first derivative, f dashed, is negative 3x squared. That is 0 when x equals 0. All right. If we look at the second derivative, all right, we're going to get negative 6x. Now, f double dashed of 0 is also equal to 0. So what we've got here is a horizontal point of inflection. Because the second derivative is 0, not negative or positive, it's 0, all right, the graph actually has a point of inflection. Right, this graph, remember cubic functions with a negative in the front go downhill first. Notice this graph's like concave up like a cup. And then somewhere over here it changes and it becomes concave down like a frown. This point over here is actually the point 0, all right, because the x value is 0. Obviously the y value, we would put 0 into the original function and we get 6. So this point here is what we call a horizontal point of inflection. The concavity of the graph is changing. Over here, it is concave up like a cup. Okay, it's positive. The second derivative is positive. Whereas over here, the second derivative is negative and the graph's concave down like a frown. Okay, using red and green. Red is a sort of negative value, green is a positive value. Okay, then this question over here says, determine the point of inflection of this graph. So how do we find a point of inflection? We make the second derivative equal to 0. Okay, so the first derivative is just 3x squared plus 6x minus 5. Right? The second derivative is 6x plus 6x. 6x plus 6. And we want that second derivative to be 0. So in fact, we get x equals minus 1. So there is a point of inflection, POI, point of inflection, at negative 1. How would we find the y value? Yeah, we'd put that value right back up in the top here, because it's a nice easy number. We can do it in our heads. That's negative 1, plus 3 is 2, plus 5 is 7, plus 2 is 9. Negative 1, 9. I'm going to draw that graph for us just to have a look at, just to confirm that. Negative 1, 9 is our point of inflection. Okay, so there the function is, and I'm going to ask the piece of software that I'm using to give us the inflection point. So I'm just typing here inflection point, okay, and the inflection point on function f. Sorry. And there it is over there, okay? And if I go and hover over that point and look at its actual points value, there it is. It's actually at negative 1, 9. And that's the point that we just found by letting our second derivative be 0. Okay, the next thing we're going to look at here is we're going to look at drawing the derivative of a function on the same set of axes. So here we've got a function f of x drawn with a black pen, okay, and we're now going to, on the same set of axes, we're going to draw the first derivative, all right, and in fact we'll draw the second derivative as well. Now, are there any points on this black graph where we know the gradient for sure? Absolutely, its exact value. Yeah, we know what's the gradient here. The gradient here is 0, which means that our parabola, remember this is a cubic, and when you differentiate a cubic, you're going to get a quadratic, a parabola. It must go through the x-axis at that same point. We also know that the gradient is 0 at this turning point. At turning points, the gradient is always 0. So our parabola is going to go through those 2 points. Now the question in our mind is our parabola going to be kind of concave up like a cup or concave down like a frown? So, and the answer to that comes from understanding at the moment over here, is the gradient of the black graph positive or negative? At this, on this piece over here, this first piece, the left-hand piece, it's negative. So our parabola, because remember the parabola that I'm drawing now, f dash of x, is going to represent the gradient of the black graph. Okay. In between these two turning points, the black graph has got a positive gradient, so our parabola must be above the axis. At the turning point, the parabola is back on the axis because the gradient of the black graph is 0. And after that, the gradient of the black graph is negative, which is why the parabola goes underneath. This green graph is the graph of f dashed. On the same set of axes, I can also draw the gradient of the green graph. Now, is there any point where we know the gradient of the green graph exactly? Halala, over here. At this point over here, we know that the gradient of the green graph is actually 0. So, and remember that the derivative of an x squared thing is just going to be a straight line. Okay, now, as we come to this point from the left, is the gradient of the green graph positive or negative? Left of this red point, it's positive. So our straight line must actually come down through here. Okay, and then it actually continues, and notice that it's negative. Okay, my piece of software decided to not want to carry on, but there we go. All right. Okay. Okay, sorry. So we kind of lost some stuff there. But this straight line basically has a positive, it's above the axis because the green graph's got a positive gradient up to that point. And then after that, the green graph's got a negative gradient. This point over here, where the second derivative, because this red graph is our second derivative, where the second derivative is 0, is also the point of inflection of our original function. Okay, notice that at this point, okay, the graph changes from being concave up like a cup to concave down like a frown. Okay, all right. Okay, here's another one. Pause the video, try it, and see if you can draw with two different color pens or a pen and a pencil or whatever. F dashed, all right, we'll do it this time. We'll draw F dashed with a blue pen, and then on the same set of axes, draw F double dashed. You can't draw them exactly, but you can get a kind of a sense of where they're going. Okay, pause the video and have a go. Okay, so let's take a look. At this point, we know that the gradient is 0. And at this point here, we know that the gradient is 0. So our parabola must go through those 2 points. Now, at the moment, is the gradient of this graph here positive or negative? On this piece, is this a positive or a negative gradient? Absolutely, it's positive. So our function, our parabola, must actually be above the axis at this point. Okay, between here and here, this line has got a negative gradient. Okay, so our parabola is now below the axis. At this point, the gradient is 0, and then it goes positive. Okay, and then, so that graph there is f dashed. The second derivative, okay, this point over here is where the gradient of the blue graph is 0. Now remember, the second derivative is telling us about the gradient of the first derivative. So it'll go through there. Over here, is this gradient positive or negative at that stage? It's negative. So this time our second derivative line actually slopes uphill. Okay, I'm going to just try and redo that, sorry. Okay, something like that, slopes uphill. And once again, this point, where the second derivative is 0, is the point of concavity. Up to there, this graph has been concave down, like a frown. Okay, but beyond there, so over here, concave down like a frown. Concave down like a frown. After that point, this graph goes concave up like a cup. Okay, right. Okay, now sometimes we get given the graph of the derivative. This is not the graph of the function, this is the graph of the derivative, and we're going to answer some questions about the function itself. We're going to ask you to try these before the next lesson, and we'll go over them then. Have a great day, everyone.